Okay, so welcome to our walkthrough of Unit 3, Worksheet number 3, which is heating curve calculations. You can see that we have our equations and our constants up here at the top of the page. Remember that Q stands for heat, M stands for mass, C stands for the specific heat, which is the amount of energy it takes to heat 1 gram of something by 1 degree Celsius. And delta T stands for the change in temperature, which is the final temperature minus the initial temperature. H in the Q equals mH equation is the heat either of fusion or vaporization, which is how much energy it takes to change the phase of 1 gram of a substance. So we're going to start with question number 1. All the questions in part 1 are heating or cooling, which means we'll be using the Q equals mc delta T, often called the Q equals mcat equation. And so for our first one, a cup of coffee, 140 grams, cools from 75.2 degrees Celsius down to comfortable room temperature of 21.3 degrees Celsius. How much energy does it release to the surroundings? Assume that coffee has the same specific heat as water. So the first thing we need to think about is our picture. So on our picture, the y-axis is the temperature, and the x-axis is the energy. In this case, the energy, because we're cooling it down, is going to be the energy that is removed from our system. And we are starting at 75.2 degrees Celsius. And we are ending at 21.3 degrees Celsius. And since it is cooling, the line will be going down. This is sort of the zoomed in part of our heating curve. Because the temperature is going down, there's a delta T, so we will be using our Q equals mcat, Q equals mc delta T equation, Q equals mc delta T. And for our numbers, mass is given in the problem. It is 140 grams right there in the problem. And then the C is specific heat. Because our temperatures here are all at the temperature that water is liquid, we're going to use the specific heat of liquid water, which we can find up here at the top in our equations, and that is 4.186 joules per gram degree Celsius. That means it takes 4.186 joules to heat 1 gram of water 1 degree Celsius. And then our change in temperature is the final minus the initial temperature. So our final temperature was 21.3 degrees Celsius, and our initial temperature is 75.2 degrees Celsius. And when we subtract these, we will get negative 53.9 degrees Celsius as our change in temperature. Notice it is negative because the temperature is going down. If the temperature were going up, it would be positive. So for our final answer, we do 140 times 4.186 times negative 53.9. And our answer should have 2 sig figs because 140 grams only has 2 sig figs. The 0 is not significant because there's no decimal point. So the answer would be negative 32,000 joules rounded to 2 sig figs. Or if you like, you can change that into kilojoules by dividing by 1,000. So it'd be negative 32 kilojoules, and that is an optional step. Okay, question number 2. So for question number 2, first step, draw the picture. The specific heat capacity of solid iron is 0.447 joules per gram per degree Celsius. If 458 grams of iron is heated from 20 degrees Celsius to 55.3 degrees Celsius, how much energy did the metal absorb? So again, we have our temperature. This time it is energy added because our temperature is going up. And we're going from 20 degrees Celsius to 55.3 degrees Celsius. So our line will be going up. And we are doing Q equals mc delta T, and it says how much energy for our problem, which means we're solving for Q. So first let's write our equation, and then we'll figure out what we should put in there. So first we put in our mass, which is given in the problem. It's 458 grams. And then we do the specific heat. Now this time it's iron, not water. Unless you're solving for it, you'll always be given the specific heat of whatever substance you need. So our specific heat here is 0.447 joules per gram per degree Celsius. And then for our change in temperature, it's final minus initial, so 55.7 degrees Celsius minus the initial, which is 20 with a dot degrees Celsius. And then when we do the subtraction for our change in temperature, that ends up being 35.3 degrees Celsius. So 458 times 0.447 times 35.3. And we will again have 2 sig figs. Because of the temperature here, it only goes to the ones place for 20 degrees Celsius and has 2 sig figs, so our temperature has 2 sig figs. So our answer would be either 7,200 joules, or if we want to convert to kilojoules, it would be 7.2 kilojoules. All right, so question 3. So for question 3, this is our first one that we will not be solving for Q, we'll be solving for something else. So suppose that during the icy hot lab, 65 kilojoules of energy was transferred to 455 grams of water at 20.5 degrees Celsius. What would be the final temperature of the water? So this time, we know that energy is being added because the problem says energy is being added. And we know the starting temperature of 20.5 degrees Celsius. What we don't know is how hot it gets. We want to know the ending temperature. That is what we're solving for. So this time, when we have our equation Q equals MCAT, we actually know Q. Q is given to us, 65 kilojoules. So Q is 65 kilojoules. But we need to do that in regular joules, so that's 65,000 regular joules. But what we're solving for, well, eventually will be T final, but first we're going to solve for delta T. So to solve for delta T, we'll divide both sides by MC. That way the MC cancels and we get delta T by itself. Delta T is equal to Q divided by mass times specific heat. And Q is 65,000 joules. The mass was given in the problem. It is 455 grams. And the specific heat, this is liquid water. So we will use the specific heat of liquid water given at the top of the page, 4.186 joules per gram per degree Celsius. And when we divide that and do the math, 65,000 divided by 455 divided by 4.186, the actual number of sig figs at the end will be 2 sig figs, but I'm including an extra one before I do my final calculation. So 4.1 degrees Celsius. That's my change in temperature, but I actually want to know the final temperature. So the final temperature is equal to the starting temperature of 20.5 degrees Celsius plus the change in temperature, 34.1 degrees Celsius, which, and then now rounded to 2 sig figs, will round it to 55 degrees Celsius. And that's because we started at 20.5 degrees Celsius, we went up by 34.1 degrees, so what we ended at was 55 degrees Celsius. All right, so the last one for this page is another one that solves not for Q. So what mass of water vapor could be heated from 112.2 degrees Celsius to 139.5 degrees Celsius if 38.2 kilojoules of energy was applied to it? So again, we were given Q this time, 38.2 kilojoules, which is 38,200 regular joules. And for our picture, we know that it went from 112.2 degrees Celsius up to 139.5 degrees Celsius. And energy was added because the temperature went up. So that's going to go up like that. And for our equation, we're using Q equals MC delta T again, as we are in this whole section. This time, though, it says what mass. So we are solving for M, which means we'll divide both sides by C delta T so that we can get M by itself. So the mass is equal to the energy divided by the specific heat times the change in temperature. And the energy was 38,200 joules. The specific heat, this is water vapor. So if you look up at the top of the page, you'll see the specific heat of water vapor is 1.996 joules per gram per degree Celsius. It's important to remember what type of water we're looking at. It's not always liquid water. And then we do the change in temperature, which is the final, 139.5 degrees Celsius minus 112.2 degrees Celsius. And when we do the subtraction there, that ends up being 27.3 degrees Celsius. So we do our math, 38,200 divided by 1.996 divided by 27.3. And this is going to have 3 sig figs. So our final answer will be 701 grams. Okay, so on the back in part 2, these are phase change problems. They're going to use our Q equals MH equation. And when we draw them, they will be a less exciting drawing because during a phase change, there's no temperature change. So you can just draw a straight line across. And the important thing to think about is which of the phase changes is this? Is it a phase change where solid is going to liquid or liquid is going to solid? So either melting or freezing, because then you'll use HF in your equation. And if it's a phase change where a liquid is going to a gas or gas is going to liquid, so that's boiling or condensing, then you'll use HV in your phase change. So for this one, suppose during volleyball practice, you lost 910 grams or 2 pounds of water due to sweating. If all of this water evaporated, how much energy did the water absorb from your body? So because it is evaporating, there's no temperature change. We're going to use Q equals MH, and because it's evaporation, we use HV. It is going from a liquid to a gas. And it is asking for energy Q, so we don't need to rearrange the equation. So our mass here is 910 grams. Oops, 910. Oops, let's just go back there. Mass is 910 grams. And HV is a constant. It's on the equations on the front, and it is 2,259 joules per gram, which means it takes 2,259 joules to evaporate 1 gram of water. And when we do the math here, there's going to be 2 sig figs because of 910 grams. That 0 is not significant because there's no decimal point. So we end up with a pretty big number that is 2,100,000 joules, or we can divide by 1,000 to do our kilojoules. That would be 2,100 kilojoules of energy, which is a lot. It takes a lot of energy to boil something. All right, so for the second one, suppose a bag full of ice at 0 degrees Celsius sits on the counter and melts to liquid water. How much energy is absorbed? Again, look, I drew it. It's an easy drawing because it is only flat. And so we're using Q equals MH again. This time we're using MHF for the heat of fusion because it is melting. And we're solving for Q because it says how much energy, so we don't need to substitute anything. So our ice is 450.0 grams. And HF is a constant on the front of the sheet. it is 334.1 joules per gram. And both of these have 4 sig figs, which means our answer will have 4 sig figs. So in regular joules, it's 150,300 joules. Or in kilojoules, that would be 150.3 kilojoules with 4 sig figs. All right, now comes the exciting part. We've got our multi-step problems. On these ones, the drawing is key because it helps us figure out how many steps will be in the problem. So for these, I prefer what I call the you are here version of drawing, where I draw an entire heating curve or an entire cooling curve and then mark which part of the heating or cooling curve I am focusing on. So for this problem, a 340-gram can of soft drink at 25 degrees Celsius is placed in a freezer where it's cooled to 12 degrees Celsius. How much energy has been removed from the soft drink for it to reach this temperature? So energy removed, I know this is going to be a cooling curve. And then we have the temperature. And before I do the specific part that I'm looking at, I'm going to draw a complete cooling curve. So a complete cooling curve, that's not a very good start. First, we cool down vapor, then we condense, then we cool liquid water, then we freeze, then we cool the solid water. So for this, we're starting at 25 degrees Celsius, which is here on the liquid water part. Remember, at the boiling point, it's 100 degrees, and at the freezing point, it is 0 degrees. And then we're ending below the freezing point at negative 12 degrees Celsius. So my picture is not to scale. This is just to show the general idea to help us figure out how many steps. So we are going to have 3 steps. Step 1 is going to be cooling down my liquid water down to 0 degrees. Step 2 is going to be actually freezing the water. And then step 3 is going to be cooling down the frozen water, the ice, to negative 12 degrees. So for step 1, we are cooling our liquid water. And since we're cooling it down, we're going to use the Q equals MC delta T equation. So that is Q1 is going to be MC, in this case liquid, because it's liquid water for the first part, delta T. So the mass of step 1, the mass of the same thing actually, the whole time the mass will be 340 grams, the mass of our soda. The specific heat of liquid water is a constant, 4.186. joules per gram per degree Celsius. And the change in temperature is just for the part that I've marked in red on the graph, not the whole thing. So the final temperature is the freezing point, which is 0 degrees Celsius. And the initial temperature is 25 degrees Celsius, which means the overall change in temperature is going to be negative 25 degrees Celsius. The temperature is going down, right? We're losing energy. So when we do the math there, 340 times 4.186 times negative 25, we get negative 35,530 joules. I'm not going to round to sig figs till the end. The negative sign there is important because energy is being lost from the system. All right, now I'm going to switch colors again because we're going to do step 2. Now step 2, I'm going to take that ice that I've now, or not, sorry, that liquid water that I've now cooled down to 0 degrees, and I'm going to turn it into ice. So step 2 is freezing. And because I am freezing it now, I am not using Q equals MCAT. I'm using Q equals MH, specifically HF for the heat of fusion for freezing. And the mass hasn't changed. It's 340 grams. And HF is a constant, 334.1 joules per gram. And so that ends up being negative 113,594 joules for step 2. And I forgot to put the little negative sign on the negative on the 334. The reason it's negative, we have to manually add the negative sign. which I forgot to write the first time. But the reason it's negative is because we are removing energy. It doesn't make itself negative the way it did with the delta T in the first one, so we have to remember to make it negative. So every step is removing energy. And then our final step. So our final step, step 3 is the part I've marked in black on there. And step 3 is cooling the ice. So we go from 0 degree ice down to negative 12 degree ice. And since we are changing temperature again, we will be using Q equals MCAT. This time though, our specific heat is for solid water or ice. And the delta T, remember, will just be for the part marked in black, not for the whole thing. So the mass here is 340 grams. 340 grams. The specific heat of solid water is 2.108 joules per gram per degree Celsius. And the change in temperature here, the final temperature is negative 12. And then the initial temperature was 0. So overall change in temperature is negative 12. And when we do the math, we get negative 8568 joules. So then our total energy is going to be all of these added together. So the Q total is equal to Q1 plus Q2. There we go. Q1 plus Q2 plus Q3. So they're all negative when we're adding them together. Negative 35,530 plus negative 113,594 plus negative 8,568. And then this only needs 2 sig figs because if you look 340, 25, negative 12, they all have 2 sig figs. So our answer is going to have 2 sig figs, and it's going to be negative 160,000 joules, or if you prefer, negative 160 kilojoules for our final answer. So on that problem, we were looking for total energy, but some problems, rather than asking for total energy, they will give us the total energy, and then we have to solve for something else. So that's the case in our second problem here. So in the second problem, we are given the total energy. So it says, suppose in the icy hot lab that the burner transfers 325 kilojoules of energy to 455 grams of liquid water at 20 degrees Celsius. What mass of the water would be boiled away? So 325 kilojoules is our total energy. And that is equal to 325 kilojoules, or 325,000 regular joules. Now we need to figure out how many steps there are to figure out what the total energy is equal to and what we're actually solving for. So in this case, since we are adding energy, I'm going to draw myself a full heating curve. So a full heating curve involves heating up ice, melting the ice, heating liquid water, boiling the water, and then heating up the vapor. So that's 0 and 100. Now on this one, we are starting at 20 degrees Celsius. So down here in the liquid water section. And it says what mass will be boiled. So that implies that we'll end somewhere in the middle of the boiling section. So we have 2 steps here. One is we need to heat up the water up to the boiling point. And then the second step is we need to boil some mass of that water. But in order to know how much mass that we have boiled, we'll need to know what Q2 is. So the total energy, since we have 2 steps, is going to equal to the sum of the energies of the 2 steps. So what we'll do is we will solve for Q1 and find the energy that it will take to heat the water up to 100 degrees. And then we'll subtract to find out how much energy is left to boil the water, and we'll use that to solve for the mass of water that is boiled. So we'll start with step 1, which is heating the water, the liquid water. And because the temperature changes, we'll use Q equals MCAT. It is liquid water, so we'll use the specific heat of liquid water. And the mass here is 450 grams. The specific heat of liquid water is 4.186 joules per gram per degree Celsius. And the change in temperature is the final, which is the boiling point, which is 100 degrees Celsius, minus the initial, which is 20 degrees Celsius. So when we subtract that, we get 80 degrees Celsius as our change in temperature, which gives us 150,480 joules as the energy used in step 1. So that's the energy to heat up the water. So now our total energy was 325,000. If we take 325,000 and subtract the amount of energy used in step 1, we'll find out the energy in step 2. So basically Q2 is equal to the total energy minus Q1, which is equal to 325,000 joules minus 150,480 joules. And that gives us 174,520 joules. So that is the amount of energy that we'll have to use for Q2. So for step 2, we are going to boil the water. But this time we are not solving for Q, we're solving for mass. So I'm going to rewrite the equation solving for mass. Mass is Q2 over HV, because remember Q equals MH. I divided both sides by H. I didn't rewrite it here just because of space issues. So the mass is going to be Q2 divided by HV, which is a constant. So our Q2 that we solved for below is 174,520. And HV, and remember it's V because it's boiling, is a constant. It's 2259 joules per gram. And if we look back at our sig figs, we'll notice that the grams only had 2 sig figs, 450 grams. So our answer will only have 2 sig figs. I can't even talk today. 2 sig figs, which means our mass is equal to 77 grams. So after we used 150,000 of the joule, or 325,000 joules to heat up the water, with the remaining energy, 174,000 joules, we were able to boil 77 grams of the water. That means all the rest of the water, 200 something grams, is still liquid. There was not enough energy to boil it. All right, one last practice problem. So on this one, 650 kilojoules of energy are added to 150 grams of liquid water at 100 degrees Celsius. What's the final phase and temperature of the water particles? So again, we are adding energy. I'm going to draw a full heating curve here. So heat the ice, melt the ice, heat the water, boil the water, heat the vapor. And man, it's really hard for me to draw straight lines on this. So 0 for melting, 100 for boiling. Remember, if it was something other than water, there would be different temperatures for that. So here we have water starting at exactly 100 degrees Celsius, so basically just before it boils. And then we want to know phase and temperature. So we may or may not have enough energy for 2 steps. We have at least 1 step and possibly 2 steps. So our first step is going to be boiling the water. Now, if that uses up all our energy, then that will be our only step. But assuming we have a little bit of energy left over, our second step will be to heat up the water. So, and we were given our total energy in this problem. So the total energy, which will be eventually the energy of step 1 and 2 added together, is 650 kilojoules, which is equal to 650,000 regular joules. This is very similar to the previous problem. We know the total energy. We're going to figure out the energy of step 1, and assuming that there's energy left over, we will then see with that energy left over for step 2, how hot can it get the water. So for step 1, we are going to boil the water. So we're starting at our phase change this time because we started right where water boils. So we're going to use our Q1 is mH and it's HB because it's boiling. And so our mass is 150 grams. That was given in the problem. And HV is a constant, 2259 joules per gram. So in order to boil all of that water, it will use 338,850 joules of energy. That is less than our total. So that means we will have some energy left over to heat up the water. So Q2 is going to be the total energy minus Q1. So the total energy was 650,000 minus Q1 is 338,000, which gives us 311,150 joules left to heat up our water. So that's going to be our step 2. This time it's going to be heating our water vapor. So I'm going to reorganize the equation. It's a Q equals MCAT equation, but we're solving for delta T here. So delta T is equal to the Q divided by mass times specific heat. So Q2, we just figured out down here, is 311,150 joules. The mass is 150 grams. This is specific heat of water vapor. Remember to always make sure you're using the correct constant. So this was on the front page. It's 1.996 joules per gram per degree Celsius. When we do the math there, 311,150 divided by 150 divided by 1.996, I get that my delta T, I'm not ready to sig figs yet because it's not quite the last step, is 1,039 degrees Celsius. The reason that's not the last step is because that is the change in temperature, but the question asks what is the final temperature. So we started, if you recall, at 100 degrees. So we have one more step. So the final temperature is equal to the initial temperature plus the change in temperature. In other words, it's equal to the 100 degrees plus 1,039 degrees Celsius. And so when we add those together, we only are going to have 2 sig figs in our final answer because of the 150 grams, which only has 2 sig figs. So although that would be 1,139, we're going to round it to 2 sig figs. So with 2 sig figs, our final answer is 1,100 degrees Celsius.